Hey, AP Chem. We are back with intermolecular forces. Last time we talked, we kind of talked through the nuts and bolts of the three different types of intermolecular forces. And then today, I want to kind of dive a little bit deeper into those different types. So, three different types of intermolecular forces. We're talking about ion dipole, 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 and London dispersion forces, also known as van der Waals forces. Okay, ion dipole forces are super straightforward. And basically what we talked about last time is about as far as they get. So today we're going to go into dipole-dipole forces a little bit deeper. So we talked about kind of the nuts and bolts of it, how a dipole-dipole intermolecular force is when two different molecules each have a dipole, and the partially positive end of one dipole is attracted to the partially positive end. Did I say partially negative? Partially negative attracted to partially positive end of a different molecule, and that causes a force between the two molecules, which is a dipole-dipole intermolecular force. Now, there is a dipole-dipole force that is exceptional, and it's so exceptional that we actually have another name for it, and that's called hydrogen bonding. So I want to talk about hydrogen bonding a little bit today. Now, it's easy to get stuck in the muck and the mire of hydrogen bonding and kind of lose sight of the big picture. And so as we're going through hydrogen bonding, I want you to remind yourself that this is just a specific example of dipole-dipole bonding. It's a specific example. It's a special example. It causes some effects that none of the other dipole-dipole intermolecular forces will cause, but it's still just a dipole-dipole intermolecular force. Okay, so let's talk about what hydrogen bonding is. So, hydrogen bonding is when your two molecules that each have a dipole that are attracting each other, when those two molecules contain hydrogen and one of three elements. So if we look at a periodic table, okay, I said it was hydrogen and one of three elements. Well, those three elements are right here. So it's where your molecules contain hydrogen and nitrogen, and or hydrogen and oxygen, and or hydrogen and fluorine. And it's these three elements for a very specific reason. So look at these three elements on the periodic table and think, what can you tell me about these three elements? What are these three elements more of or less of than any of the elements on the periodic table? Might be a good place to pause it and think and jot some notes down. And this really gets back to the periodic trends, right? If we think about the periodic trends, these three elements are some of the smallest elements on the periodic table, right? Atomic radius is going to decrease left to right. It's going to increase top to bottom. So if we look at where the smallest elements are, they're in this corner. These are some of the smallest elements on the periodic table. Hydrogen is also one of the smallest elements on the periodic table. Okay, if we look in terms of electronegativity, increases left to right and decreases top to bottom. So if we look at where the most electronegative elements are on the periodic table, it's right there in this corner. So these three elements are some of the smallest and most electronegative. So if you think about it in terms of a hydrogen approaching these elements, if we're thinking about fluorine, for example, okay, fluorine is going to have a 9+ effective nuclear charge, it's going to have two energy levels that are both fairly full of electrons. Okay, so if we think in terms of another electron approaching fluorine, that other electron can get really close and is going to be really strongly attracted to that atom. So it's going to be really strongly attracted because of the protons, right? It has the most protons, but it's also going to be really highly attracted because that element is small. And remember, if we're talking about Coulomb's law here, force of attraction is going to be proportional to the number of protons. That's Z. Z is the nuclear charge. And also it's going to be, force of attraction is going to be inversely proportional to distance squared. So as distance gets smaller and protons get bigger, we get this giant attraction, this force of attraction that is unusually high. Now we're taking these elements and we're pairing them with hydrogen. Let's think about hydrogen real fast. Hydrogen only has one proton. So hydrogen is not very attracted to its own electron, right? Hydrogen is also small, so that electron that belongs to hydrogen can stay close to the nucleus of hydrogen and close to the nucleus of nitrogen, oxygen, or fluorine at the same time. And so we end up with these dipole-dipole forces between molecules and other molecules that contain these elements. We end up with dipole-dipole forces that are exceptionally strong. So let's return to our slide, and we can talk a little bit more about that. So remember, we're talking about dipole-dipole forces. We're not talking about forces within the molecule. We're not talking about forces that are bonding oxygen to hydrogen, right? We're talking about forces that are attracting one water molecule, the hydrogen, or the partially positive end of hydrogen, to oxygen on a different molecule, that partially negative end of oxygen on a different molecule. So not only is the bond strong, but the intermolecular force between these two molecules is going to be super strong also, right? That hydrogen from molecule 1 can approach the oxygen from molecule 2 very closely. Hydrogen on molecule 1 is going to have an extremely large partially positive force. These electrons are going to be pulled almost completely to oxygen. And oxygen on molecule 2 is going to have an extremely large partially negative charge. So it is an intermolecular force, right? It's a force between two molecules, but these partial charges are almost complete charges attracting across two different molecules. So it's going to result in an exceptionally large and exceptionally strong intermolecular force. A couple other examples of where this can happen would be ammonia. So ammonia looks something like this. Right? And then another ammonia that looks similar. Okay, so if we're talking about attraction, this nitrogen is going to be partially negative. And again, that it's dealing the nitrogen, which is strong and packed full of protons, is going to be compared in its bonding dipole to hydrogen, so it can pull that electron almost completely away from hydrogen, resulting in a very large partially negative charge, almost a complete negative charge. And then on the opposite end, we have this other molecule of ammonia. Again, that electron is pulled almost completely away from hydrogen, leaving a partially positive charge that's almost a complete positive charge. So we get this really strong attraction between these two. Another example would be HF. And very similar things happen inside HF. Inside the actual molecule, the electron gets almost completely pulled away from hydrogen, leaving fluorine, both a small atom with a lot of electronegativity. It's going to have a very large partially negative charge, probably almost a complete negative charge. Hydrogen, partially positive. That electron gets pulled almost completely away from hydrogen towards that fluorine, leaving it with a partially positive charge that's extremely large, and you get a very strong intermolecular force between these two molecules. Now, our three examples I'm showing you are pure substances, but you can also get mixtures. You can get water attracted to ammonia. You could get hydrogen fluoride dissolving in water. You could be talking about a mixture as well. But in any case, it's hydrogen bonding is going to be from the hydrogen on one molecule to oxygen, nitrogen, or fluorine on the other molecule. And within the molecule itself, you have to have a hydrogen and then oxygen, nitrogen, or fluorine within the molecule itself. Okay, so all of that to say, it results in extremely large intermolecular forces, extremely strong intermolecular forces. And when we say extremely strong, what we're meaning is compared to other similar molecules. So if we look at water, for example, let's go back to the periodic table. So if we look at water, it's H2O, right? H2O is water. Well, what would similar molecules be? Similar molecules would be molecules formed within the oxygen family. So H2S would be comparable. H2SE would be comparable, and so on and so forth. So if we look at this graph right here, look at molecular mass on the bottom. So this is molecular mass increasing from low molecular mass to high molecular mass. Look at the Y here. This is temperature, and this is going to be the melting point. Okay, so here we have similar molecules within that family. So H2S, here is the melting point for H2S, H2SE, H2TE, H2PO, and we see a general trend, right? It's fairly linear. It's not perfectly linear. It's fairly linear as molecular mass increases. The melting point also slightly increases. We can attribute that to London dispersion forces as these elements in the oxygen family get larger with more electrons attached. You can form that instantaneous dipole, and you're going to get bigger London dispersion forces that happen because of those instantaneous dipoles. So not only do we have dipole forces occurring here, we also have London dispersion forces occurring here. And we see this nice little trend until we get to water. Water should be here, right? Water should continue this trend. Lower molecular mass should have a lower melting point, but that's not what we see. Water totally breaks the trend. Water's melting point is up here. It is an outlier on this trend chart because it doesn't have weaker intermolecular forces leading to a lower melting point. It has exceptionally strong intermolecular forces because we're not talking about simply dipole forces. We're talking about a hydrogen bonding dipole force. That's what we mean by exceptionally strong. You can see for, they have a similar trend here for molecules that form within the carbon family. And you can see that they also have this nice little trend going on here. Carbon also slightly breaks the trend, but it's nowhere near the trend break that occurs with water. Right? Carbon also is smaller. That diminishing size can attribute to some unusually strong intermolecular forces, but it's nowhere near the trend break that we see with this hydrogen bonding that's occurring. Okay, so here's a nice little summary for us. So due to hydrogen bonding, why do we care about this exceptionally strong dipole-dipole force? Well, here's your definition of it. It's an intermolecular force between the hydrogen atom and a near small electronegative ion or atom. Again, it has to be fluorine, oxygen, or nitrogen. Because of the high electronegativity, that bond inside the molecule is extremely polarized. It's probably the most polarized bond you can get before turning ionic. And so this hydrogen here is small and naked, practically naked. Its electron has practically been taken from it. It can approach very close to another small electronegative atom that is on a molecule near it. It's still going to be weaker than a chemical bond. So this intermolecular force that occurs right here in green is still going to be weaker than the polar covalent bond that happens inside the molecule itself. So notice that they're both forces between a hydrogen and an oxygen, but one is describing a hydrogen-oxygen inside the molecule. One is describing a hydrogen-oxygen force that is between two molecules. So the one inside the molecule is still going to be stronger than the one between the two molecules. But it is the strongest intermolecular force that we know about, and it drives a bunch of things. Without hydrogen bonding, we would not have life on Earth. Hydrogen bonding is what causes bonding inside DNA, causes those, ADP, adenosine, I don't know. For crying out loud, let's figure this out. Haha, I'll do you one better. I'll get you a picture. All right, so you can see the A, T, G, and C ends of those nucleotide units. They are hydrogen bonded to the A, G, C, T end of the nucleotide units on the other strand of DNA. And so it's hydrogen bonding that holds these two strands together and then results in that double helix. Also, hydrogen bonds are responsible for many of the necessary bonds that cause the formation of animal tissue. Same thing with a lot of the different properties of water, the density of water, the surface tension of water, the fact that when water freezes, it expands. Most things don't do this, right? As energy is removed and the temperature decreases, most things start moving slower and they actually condense, right? The solid should be more dense than the liquid, but that doesn't happen with water. As water molecules lose energy and start to move slower, what they do is they form these hydrogen bonds that they're slipping past when they're in the water state and they're moving around. These hydrogen bonds actually form very specific crystals, very specific angles, very specific bond lengths to each other. And if you give the water enough time to actually find these ideal bond lengths in this hydrogen bonding, water will actually expand to form a very specific crystal that is ice. And so frozen water is less dense than liquid water. And why is this important to life? Can you guys tell me an example of why this is important to life? What would happen if water sank as it froze? If you think about like a pond or a lake or an ocean, right? If water sank as it froze in the ocean, ice would form, sink to the bottom, and raise the ocean level. And then ice would sink to the bottom, and raise the ocean level. Ice wouldn't be there to reflect sunlight back out. It would just be dark water absorbing the sunlight. And even if something was there to reflect out the sunlight so that the water kept freezing, the ice at the bottom of the ocean would never melt. And so we would lose this cycle. Same thing with a pond. Think about a pond. We have water and we have happy fish that live inside our water, right? Okay, well, when it starts to snow, on top of this pond forms this insulating layer of ice, right? And our little happy fish can stay happy inside the pond all winter long. If this didn't occur, if ice would freeze and sink, then our little happy fish would turn into a little fishsicle and would not be happy and alive anymore. It would die. It would get frozen, right? So there's a whole lot of properties of water that are dependent, that occur because of this hydrogen bonding. There's a whole lot of hydrogen bonding that occur inside living organisms and enable life to be. So it's a really cool phenomenon. It's a really interesting intermolecular force that has implications all over science. Also, as water freezes, it's pretty fascinating to watch like the crystals of ice form, snowflakes form because of hydrogen bonds. If you've ever noticed that your water freezes cloudy sometimes and clear at other times, that has to do with the time that the ice has to form those hydrogen bonds and the crystal structure and the order of the crystal structure that results. So it's all very fascinating. If you go into science, science in any field, you will deal more with hydrogen bonds, and it's always interesting. Okay, we'll do some practice with that. That basically is my pitch on hydrogen bonding. I want to talk about London dispersion forces a little bit more. Okay, so London dispersion forces, remember, London dispersion forces are what exists in between nonpolar molecules when they exist as liquids and solids, right? It's why we, the fact that nonpolar molecules form liquids and solids is our argument for the existence of London dispersion forces. But fun fact, London dispersion forces don't only exist in between nonpolar molecules. In fact, they exist in between every molecule. And you just saw that on the last page when I was talking about the trends that occur with like Si, H2Si, H2Se, H2 TE, H2PO, that whole trend that was occurring within oxygen's family when it bonds with hydrogen. The difference between those melting points can be attributed to London dispersion forces. London dispersion forces happen anytime two molecules interact. So one of the favorite questions on the AP test is, what intermolecular forces are present? And you should always list London dispersion forces. Just list it first. You just automatically write down LDF, and then you stop and you evaluate, okay, what else is going on? Are there ion dipole forces here? Are there dipole forces here? Is there hydrogen bonding here? So list London dispersion forces automatically, and then go back and analyze and list out anything else that may exist there. Like we said yesterday when we were talking about London dispersion forces are going to change based on mass and shape. So for example, if you have the halogens, let's go look at the periodic table and look at the halogens. Okay. If we're talking about London dispersion forces that are occurring among the halogen molecules, right? As the halogens get bigger, going top to bottom in this table, you're going to have more and more London dispersion forces. So London dispersion forces on iodine are going to be stronger than London dispersion forces on fluorine because iodine is bigger. Iodine has more mass. Iodine has more electrons, and therefore it is what? It is squashy. My favorite word. It's squashy. So mass impacts London dispersion forces. If you're comparing two molecules and you're trying to figure out why the boiling point is different or why the melting point is different or why one forms a solid and one forms a liquid, one of the things you should compare is its mass. Is it bigger? If it's bigger, it's going to have stronger London dispersion forces. The other thing you should look at is the shape of the molecule. So, and this is really common among organic molecules. So we can look at, let's see, if we look at C5H, I don't know. Let's draw this out. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C5H12. Okay, we can write a molecule with 5 carbons a couple different ways, right? We can write it like that. That would be pentane. We can write it like 1, 2, 3, 4. That. That would also be C5H12. It'd just be a different isomer of C5H12. Okay, so if we compare these two molecules, they are going to have different London dispersion forces because one of them is more compact and one of them is non-compact. So the molecule that is less compact is more able to have its electrons kind of thrown from side to side. So the one that is less compact is going to have stronger London dispersion forces. So again, if you are comparing two molecules and you're trying to figure out what the difference in their property is, why do they have different melting points? Why do they have different boiling points? Why do they have different states of matter at STP? Their shape could impact that. Now, you do have to be a little bit careful because when you're comparing organic molecules, not only can you compare isomers to each other, but you can also start to add on functional groups. So this would be a really good time in our life within AP Chemistry to take a minute and go back and review those functional groups that we've talked about. Alcohols are super common. Amides are very common. Carboxylic acids are very common. Sometimes they throw in esters or ethers. So what you have to look at when you're looking at these functional groups is polarity. You have to be aware of polarity. If they're going to throw an alcohol group onto one of these, okay, all of a sudden it goes from being a nonpolar molecule before the functional group was added to being a polar molecule after the functional group was added. So you have to be aware of functional groups changing the polarity of molecules. And then all of a sudden you're going from looking at London dispersion forces to looking at London dispersion forces with dipole-dipole forces. So shape makes a difference. Less compact will have stronger London dispersion forces. But be careful when you're comparing shape, and always be aware of functional groups, because if they change functional groups on you, that's going to make more of a difference than just changing the shape all by itself. All right, so let's generalize intermolecular forces here. So first of all molecules experience London dispersion forces. In fact, about 80% of all intermolecular forces are due to London dispersion forces. So if they ask you what kind of intermolecular forces are present, the very first thing you should list is London dispersion forces for every molecule. Dipole that then accounts for the rest of intermolecular forces. With equal mass and shape, London dispersion forces are going to be approximately equal. So if the mass and the shape are equal, then you can the London dispersion forces will be a wash. And then you need to look for other types of intermolecular forces that make the difference between properties. Do they have ion dipole forces? Do they have dipole forces? Are some of those dipole forces hydrogen bonding? That can attribute to the rest of property differences. If, however, you have similar formulas and you have two different shapes, London dispersion forces can make the difference in the properties between those two shapes. Similarly, if you have similar structures, similar compounds, like the family that we looked at, H2S, H2SE, H2TE, I think, H2PO. If you have similar molecules that form and the mass is different, all of these are H2 something. I'll put an N. Oh no, N is nitrogen. I'll just put an X. Usually when you have an X, you're talking about a halogen, but I'll put a Z. There we go. Okay, notice that H2 is always the same in this compound, but the Z is different. The Z is one of the picks from the families. If this is the case, then your mass is going to make the difference. Polonium is the biggest molecule. It's the biggest element. It has the biggest mass. So it's going to have the greatest London dispersion forces. Therefore, if the intermolecular forces are stronger, it's going to take more energy to break them, and your melting and boiling points are going to be higher. Okay, so that's where a lot of the test questions come from when you're looking at intermolecular forces. Intermolecular forces are everywhere. They influence a whole lot of stuff. Usually on the test, they're going to ask you what intermolecular forces are present, and they're going to ask you to tie the idea of like stronger or weaker intermolecular forces to these property changes, phase changes, melting point, boiling point differences. Okay, so we will look at some of those and practice some of those together. The next place we're going to go is kind of a throwback. We're throwing back to chapter 11. Now, you did read and outline this when we went through chapter 11. It's from 11.2. And in 11.2, what they do is they take the idea of solubility and solution formation, and they explain it in terms of intermolecular forces. So let's talk through this, and then we can do some practice with this in class as well. I also want you to go back and look at these questions from the book. There's 5 questions. They're through question 47 to 57, odds only. Once we talk through this, I do want you to go back and try some of these questions and see if you can explain solubility in terms of intermolecular forces, now that we have talked about intermolecular forces. Okay, so remember when we talked about solubility before, we talked about this general principle of like dissolves like, right? Polar things are going to dissolve into other polar things. non-polar things are going to dissolve into other non-polar things. And now you can kind of start to see why polar things are attracted to other polar things, because a polar molecule is going to have a dipole, and that dipole is going to be attracted to other dipoles and other polar things. There's definitely going to be an attraction there, and that attraction is what dissolves solubility. But it's not quite as simple as that. When we look at solubility, we have to look a lot of times in terms of what happens to the solid before it can have, though, that ion or that dipole present in order to dissolve in the other polar thing. So we want to look at solubility as if it's occurring in 3 separate steps. Okay, and the separate steps would be listed down here. 1, 2, 3. So first of all, usually you're dealing with a solute dissolving into a solvent. So the solvent is usually polar, like water, right? Water is our universal solvent. And usually we're going to have a solute dissolve into that. So our solute, for example, if it's sodium chloride, right? Our favorite one to talk about. It's simple, it's cheap, it's common, we all understand it. Okay, so sodium chloride is not just a discrete molecule. It's not a sodium attached to a chlorine floating around happily in space. It's a lattice, right? We have positives, which are our sodium, attached to negatives, and we should have an equal amount of these things. If I add one more row, does that make them equal? I think so. Yeah. Okay, so we'll go with this. This is our lattice. We have positives attached to negatives, and we have directional ionic bonds occurring that are holding this lattice into place. Okay, so this lattice is not polar. This lattice is neutral. This lattice has positives and negatives that are already stabilizing each other. We don't have a dipole over this compound, over this lattice. Remember, it's this huge crystal structure. And so the first piece of energy that we really have to take into account here is separating the solute into its individual components. So if we're taking our solute, our lattice of sodium ions and chloride ions, and we're going to separate them into individual components, individual sodium ions, individual chloride ions, is that going to take energy or release energy? It's going to take energy. So this would be H1. It's going to take energy. It's actually going to take a lot of energy. We're going to have to overcome these ionic forces inside this crystal in order to separate it into components. Okay, second of all, we have to overcome intermolecular forces in the solvent itself to make room for the solute. So we have water down here, and remember, this water is pretty organized, right? It is at happy distances away from each other. It's oriented so that the dipoles line up. It is in motion, but it's a fairly organized liquid because of the dipoles that are present. And so before the solute can fit inside, we actually have to expand this solvent. We have to move those water molecules farther away from each other in order to make room. So is that going to take energy or release energy? Well, this also is going to take energy. Probably not as much energy as separating our solvent into components, right? That's probably going to take more energy. Since H1 is overcoming ionic forces, H2 is overcoming dipole-dipole intermolecular forces. H1 is probably going to be bigger than H2, but they're both going to require energy. And then H3 would be allowing the solute and solvent to interact. That would be H3. So that's the formation of the solution. So would that take energy or would that release energy? So if we're bringing these ions and dipoles that are stabilizing each other right now into contact, then and allow them to interact. That's going to lower the energy of the system. So we're probably going to get a lot of H3 out. Okay, so that's kind of what our energy diagram would look like in the formation. Now, if the way that I've drawn it, it looks like it's an endothermic. If we get all of this energy out, then it could be exothermic. That's going to depend on what your solute and your solvent are. Okay, so if we look at this, here it is on a molecular level. We have, in this first graph, we have step 1 separating the they have step 1 is separating the solvent. That would be making space inside our water. They have step 2 as separating their solute into individual components. And then they have step 3, creating the solution. They also have it over here. What's the difference between the two graphs? The difference between the two graphs is whether it's an exothermic or an endothermic formation of your solution. Okay, so when we get back together, we're going to talk about this in terms of a couple specific cases. What does this look like when we combine oil and water? And do we have a solution that forms in that case? And why? Can the energy differences explain why that solution does or doesn't form? And then we can look at this solution that we've been talking about of sodium chloride. Does that solution form and why? Can we explain the solution formation in terms of these this energy difference? Okay, so we'll talk about that when we get back together. For now, this is a good stopping point. We'll stop here. Let me know what questions you have. I'll see you in class.